Edge AI has to prove itself on real devices, survive real deployment constraints, and keep working after release. This chapter focuses on those practical steps because accuracy alone is not enough at the edge. Evaluating a system means deciding how well it meets its goal, and that judgment depends on what you choose to measure. The same system can look good or bad depending on a metric, so the first step is always to pick the right way to judge it. Evaluation needs to run through the whole Edge AI lifecycle, not sit at the end as a final checkpoint. The point is to keep asking whether the system still behaves correctly as it moves from lab work to hardware, deployment, and field use. A one-time pass or fail check is not enough once real sensors and real users enter the picture. The model can look strong during development and still degrade when power limits, hardware differences, or operating conditions change the environment around it. The useful question changes with the stage of the project. Sometimes the evidence is about one component, sometimes the whole pipeline, and sometimes a live device under realistic conditions. So evaluation has to match the situation being tested. A system rarely has a single definition of success. Latency, missed events, power use, adoption, fairness, and maintenance costs can all matter at once. And making those criteria explicit keeps the team from optimizing the easiest metric instead of the right one. A simple manual process or rule-based alert gives a reference point. If the new system cannot outperform that baseline on the situations that matter, it has not yet justified replacing it. Component-level testing catches failures that end-to-end scores can hide. Each stage needs its own check because a model, a sensor pipeline, and a post-processing rule can all look fine separately while the combined system misses the events it was built to detect. Once the parts are connected, the behavior changes. A threshold may be too strict in real noise, or a smoothing step may delay warnings too long. So integrated testing tells you whether the pipeline still works as a system and not just as a diagram. Controlled simulations let the teams stress the system with runoff, rain, algae blooms, and noisy readings that were missing from the original data. That does not replace field testing, but it does surface weak spots before mistakes become expensive on deployed hardware. Edge hardware changes more than speed and size. Sensors differ, chips differ, timing differs, and environmental conditions like dust, vibration, and moisture can reshape the input before inference ever begins. So optimization choices need to be checked on the actual device. Actual hardware testing asks whether the system still works under real operating conditions. A device can look correct on a bench and still fail beside a stream because of drift, battery limits, or weak connectivity, so laboratory results alone are not enough evidence. Deployment needs its own judgment process. Releasing a new build gradually lets the team compare versions, catch regressions, and roll back if production behavior gets worse, which makes rollout part of the evidence rather than a separate administrative step. User testing matters because a technically accurate model can still fail the workflow. If alerts are confusing or overwhelming, people stop trusting them, and that human reaction can be enough to make the system ineffective in practice. Responsible evaluation has to look for subgroup gaps and context shifts. If performance changes across sites, weather, mounting patterns, or user groups, the team needs to see that early so the system does not become a trusted tool with hidden blind spots. Different stakeholders will want different outcomes, and those goals will collide. Sensitivity, false alarms, model size, and ease of use all pull in different directions. So good evaluation makes those trade-offs visible instead of pretending they do not exist. Teams need people who can prove a system works in context, not just that training succeeded. That means knowing what evidence belongs at each stage, what hardware tests are essential, and what has to keep being monitored after release. The right evaluation mode is a design choice with operational and ethical consequences. As the workflow continues, the next question is which metrics fit which tasks, how deployment itself becomes evidence, and how monitoring keeps that evidence alive after launch. Evaluation matters because it answers the practical question of whether an edge AI system should keep moving, stay in iteration, or be held back. The right method depends on the decision you need to make, so the same test is not useful at every stage. Early on, evaluation helps decide whether a component is worth keeping. Later, it checks whether the parts cooperate, and before rollout, it supports a go or no-go call under real constraints. A benchmark can be perfect for one question and misleading for another. A clean lab score may hide field failures, while an expensive field trial may be unnecessary if simulation already exposes the main risk. Failure is often fastest to find at the component level, where you can isolate one part at a time. That makes this stage useful for locating where trouble begins before the mistakes spread through the pipeline. Start with the sensor stream, then pre-processing, model response, and thresholding logic. Each layer can be checked on its own, which is much easier than diagnosing a fully assembled system in the field. That narrow focus is the strength of component tests, and also their limit. A feature extractor can look excellent on a clean subset while the full pipeline fails once timing, noise, or ordering become messy. Once the parts look workable, the question changes to whether they still cooperate under real operating conditions. At this stage, readiness depends on interaction, not just isolated performance. Integrated evaluation checks the whole chain: cadence, pre-processing, inference, post-processing, and alert logic. A module that looks strong in a notebook can become brittle when it has to share timing, memory, and power with the rest of the device. Latency, battery drain, memory pressure, and buffering all affect whether a correct model is actually usable. System-level success is more meaningful because it includes those constraints, not just model accuracy. When live testing is costly or risky, simulation becomes the middle ground. The goal is to push the system with conditions that resemble the field closely enough to expose likely failures. That means noisy inputs, intermittent connectivity, degraded sensors, and awkward timing. For a remote device, replaying realistic sensor sequences can uncover problems without sending a team out every time. Simulation is valuable when the cost of a mistake is high, but it still remains an approximation. If the assumptions are too neat, the test gives false reassurance instead of real warning. Controlled testing eventually has to meet real use, because correctness and human experience are not the same thing. QA asks whether the system behaves properly. Usability asks whether people can actually live with it. A system may behave as designed and still confuse users, tire them out, or invite mistakes. That difference matters most when people depend on the system every day. Class imbalance makes this easy to miss. Overall accuracy may look strong, while recall on the rare failure class stays poor, which means the system misses the events it was meant to catch. A wake-word model can look sharp in a quiet lab and become annoying in a noisy room. Usability testing reveals whether false activations and missed activations stay acceptable when microphones, background noise, and speech conditions change. Deployment discipline becomes the main issue when rollout itself can create risk. In that setting, evaluation has to support safe release, not just technical correctness. A limited release lets the team observe production behavior without exposing the entire operation to one failure mode. It also gives room for rollback planning, version tracking, and operational support. A remote, resource-limited device needs realism and field approximation. A production inspection system needs release control and support discipline. The method should match the kind of risk that matters most. Evaluation choices also carry ethical weight because they decide whose problems show up in the evidence. A narrow test can hide uneven error and make a system look safer or fairer than it really is. If the data underrepresent a subgroup, reliability gets overstated for the population that matters. If the metric only rewards aggregate performance, it can conceal a pattern of unequal mistakes. Component tests help with debugging. Simulation helps with stress. QA checks correct behavior. Usability checks human experience. And staged rollout reduces risk. The choice matters because a method is only useful when it matches the question being asked. A strong production skill is being able to justify metric choices and explain why lab results may diverge from field behavior. That kind of judgment tells a team whether to iterate, optimize, release carefully, or hold back. Evaluation is not one final gate at the end of development. It is a set of methods with different evidence value and different operational consequences, and choosing well is what makes deployment confidence trustworthy. Metrics decide whether a model is getting better in the way that matters. The goal here is to learn how to choose measures that match the task, the risks, and the deployment setting. A metric is only useful if it pushes the system toward the right outcome. If the score is poorly chosen, optimization can reward a number that looks good while the real field behavior gets worse. One number never captures everything. In Edge AI, the measure has to match the task, the device limits, and the cost of being wrong. Otherwise, the evaluation gives a false picture of performance. Loss is helpful during training because it gives the optimizer a direction to reduce error. But a low loss does not guarantee that the model will behave well on a limited device or under real input conditions. Riverwatch Node shows the risk clearly. A model can look solid on balanced data, then miss rare warning cases after deployment. Overall accuracy can stay respectable because the easy class dominates, even when the important class is being missed. The first question is whether the class labels are being judged in a way that reflects the real cost of mistakes. Start with the broad score, then move into the error structure that explains it. Accuracy counts correct predictions, so it is fine for a quick check on balanced data. Once one class becomes much more common, the number can look strong even if the model is failing on the minority cases. A confusion matrix breaks the score open and shows where the mistakes are happening. That makes the asymmetry visible, so you can see whether the model is good on ordinary cases but weak on the alert class. The same model can look healthy on a balanced set and look much weaker once the class distribution shifts. That is why the meaning of the metric depends on the evaluation data, not just the model itself. Averages are convenient, but they can wash out the class you care about most. Per-class views keep that failure from disappearing inside one number. Precision asks how trustworthy a positive prediction is. Recall asks how many real positives the model manages to find, and those are different questions with different consequences. Once the definitions are clear, the formulas make the relationships precise. They show how each rate is tied to one part of the confusion matrix. Precision measures how many of the things the model called birds really were birds. A high precision score means fewer false alarms among the positive predictions. Recall measures how many real birds were actually found. If recall is low, the model is missing targets, even if its positive predictions look clean. True positive rate is another name for recall in binary classification. It tells you how often the class of interest is correctly caught. False positive rate measures how often negatives are incorrectly labeled as positives. In some systems, that error is expensive because it creates unnecessary alerts or actions. True negative rate shows how well the model ignores things it should ignore. It is the complement of the false positive rate. False negative rate measures the missed positives. When a positive class is important, this rate is often the one that hurts the most. A bird classifier makes the trade-off easy to picture. Predicting bird too often gives false alarms, which hurts precision. Missing birds altogether hurts recall, because the system fails to notice the class it was built to detect. A model score is not yet a decision. The threshold is what turns that score into positive or negative behavior, and changing it changes the balance of errors. A pair of scores like this shows the model leaning toward one class, but not by much. The raw output still needs a decision rule before it becomes an action. Raising the threshold can protect a sensitive system from unwanted activations, which often improves precision. The trade-off is that some genuine positives get rejected, so recall can drop as well. These rates matter because they describe the direction of the mistake, not just the total number of mistakes. That makes it easier to connect the metric to the cost of an error in the field. When one summary number is useful, F1 is often chosen because it balances precision and recall instead of favoring only one of them. The harmonic mean pulls the score down if either precision or recall is weak. That makes F1 stricter than a simple average in cases where balance matters. Single number summaries are convenient, but they hide the individual error types. If one model shifts toward recall and another shifts toward precision, the summary can blur the difference even when the application cares a lot about that trade-off. The ROC curve traces how false positives and true positives move as the threshold changes. AUC compresses that curve into one value, which is useful, but still leaves out the full class-level error picture. Not every model predicts classes. When the output is numeric or when the task includes localization, the metric has to measure a different kind of success. For a regression model, the question is how far the prediction is from the target value. That is why metrics like MSE, and RMSE focus on error size rather than class agreement. MD gives a direct average error measure. It is easy to interpret because it stays close to the actual scale of the target. That kind of number is immediately usable in practice. A 10-gram miss might be fine for one application and far too loose for another, so the acceptable metric depends on the decision being made. MSE emphasizes larger mistakes because each error is squared before averaging. That makes big misses count more heavily than small ones. The source equation is preserved here, but standard RMSE is the square root of MSE. In practice, RMSE is often discussed because it keeps the error in the target's units and is easier to interpret with stakeholders. The important choice is not which metric sounds most advanced. It is whether the metric matches the consequence of being wrong and tells you something useful about the model's behavior. Detection adds another layer, because the model must find an object or event and place it correctly. That means the metric has to reflect both recognition and localization, not just one or the other. On the edge, the hardware becomes part of the evaluation. A model can be accurate and still be a poor deployment choice if it is too slow, too large, or too hungry for power. These runtime metrics tell you whether the model can actually live on the device. Accuracy alone does not matter if the system cannot fit, cannot respond in time, or drains the battery too quickly. Latency covers everything from capture through inference to post-processing. For streaming systems, that delay determines whether the model can keep up with live input. A smaller model often helps, but it is not the only factor. A costly pre-processing step or weak device can dominate the runtime and erase the gain from model simplification. Memory budgeting has to include the model, buffers, and the rest of the system on the device. Even a strong classifier fails the deployment test if it cannot fit inside the available RAM and ROM. Battery life depends on how long the device stays awake, how much current it draws, and how large the battery is. In a field node, those constraints interact directly with the model's workload and the sensor schedule. Engineers need to defend metric choices and explain why one score was not enough. Being able to connect accuracy, threshold choice, recall, and hardware limits is part of speaking the language of production. A good system is the one that behaves correctly under the conditions it will actually face. That means the metric has to reflect the task, the decision threshold, and the limits of the device at the same time. Metric choice affects what the system learns, how it is evaluated, and whether it can actually ship. The goal here is to connect the score on paper to the decision the device must make. A good score is not the one that sounds impressive. It is the one that exposes the error the system must avoid. Once that match is clear, the same metric can guide training, validation, and deployment without lying to you. Metric selection belongs in the implementation plan because it changes thresholds, reporting, and even hardware trade-offs. The number you track shapes the behavior you get. For a classifier, the real questions are about uncertainty, imbalance, and the threshold that turns a score into an action. For a regressor, the question is whether the error size means anything in the units the operator cares about. On edge hardware, latency, RAM, duty cycle, and battery use become part of the same evaluation. One metric should answer whether the system is good enough, and another should explain where it fails. That pairing keeps a model from looking fine overall, while still hiding expensive false alarms or missed events. Probabilities are not yet decisions. They become decisions only after a threshold or class rule is applied. That threshold changes the measured behavior of the model, so it has to be treated as part of the metric design. Many edge classifiers output confidence scores first and labels only after a cutoff is chosen. That cutoff is not a cosmetic setting. It determines which errors are counted and how the final performance looks. A simple two-class example makes the threshold effect easy to see. Once the model gives scores, the final label depends on the rule used to interpret them. A score like this says the model leans towards sick, but it is still just a score. Whether that becomes a sick decision depends on the cutoff you choose. With one threshold, the same case becomes sick. With a stricter threshold, it becomes healthy. That change moves precision and recall in opposite directions. So threshold tuning is really metric tuning. When failures are rare, a lower threshold can catch more true events, but usually creates more false alarms. In a battery-powered device, those extra wake-ups cost energy as well as trust, so the right threshold is the one that matches the real cost of the mistake. Class averages can hide the classes that matter most. Per-class evaluation shows whether the model is actually helping the rare or expensive cases, not just the majority class. With imbalanced data, a model can score well by doing a decent job on the common class and still neglect the rare one. That is why accuracy alone is not enough when the class mix is skewed or the error costs are different. The confusion matrix makes the failure pattern visible row by row and class by class. If the rare class is being missed, precision, recall, and F1 tell a much more honest story than a single average score. These three quantities describe different parts of the same error picture. Precision asks how many predicted positives were correct, recall asks how many real positives were found, and F1 combines both when one number is needed. Precision measures purity in the predicted positive set. High precision means the model is making fewer false positive claims among the cases it labeled positive. Recall measures coverage of the real positive cases. High recall means the model is finding most of the events that truly exist. F1 balances the two sides into one score, so neither precision nor recall can dominate completely. It is useful when the rare class matters and you need one summary number without losing sight of the trade-off. F1 is helpful, but it still hides the exact pattern of mistakes. The confusion matrix tells you which class is being confused with which other class, and that detail is what you need for debugging and calibration. Regression brings the units back into the evaluation. The right score depends on what the predicted number means in the real system and how costly the error is in those same units. MNE stays in the original unit, so it is easy to interpret when the output is temperature, weight, or distance. MSE and RMSE punish larger misses more strongly, which helps when big errors are much more harmful than small ones. A numeric error only matters relative to the application. The same miss can be acceptable in one setting and unacceptable in another, so regression scores always need context. Different tasks reward different kinds of evidence. The metric family should match the decision, the error cost, and the constraints of the device that will run the model. A task should point to the metric, not the other way around. Once the task is clear, the choice of score becomes much easier to justify. Accuracy works only when the class balance is fairly even and the mistakes cost about the same. Once imbalance or asymmetric cost shows up, class-specific measures become the safer way to judge the model. Regression metrics should reflect both the unit of the prediction and the penalty you want for large misses. ME is easy to read, while MSE and RMSE make larger errors count more heavily. Detection tasks are really about event trade-offs. You need to know what gets missed, what gets falsely triggered, and which threshold produces that behavior. On constrained hardware, runtime matters just as much as model quality. A model can be mathematically strong and still fail if it uses too much memory, responds too slowly, or drains power too fast. Edge deployments make this constraint very concrete. If the device wakes briefly, samples, runs inference, and sleeps again, then compute time and energy budget may matter more than a small gain in accuracy. Those limits influence the model family, the input size, the threshold rule, and sometimes even whether the feature extractor can stay on device. In practice, the metric set becomes part of the design space. A field device like Riverwatch Node forces all the metric questions into one place. The same system has to respect class errors, thresholds, latency, and power use at the same time. For Riverwatch Node, rare events may need a recall target, false alerts may need a precision target, and battery budget may limit how much inference time is acceptable. A small improvement in F1 is not useful if it costs too much wake time. Freshline Inspector adds another production concern: traceability. When many devices are in the field, the team must know which firmware, model version, and threshold produced each result so comparisons stay trustworthy. A metric pipeline should stay consistent from training through validation and finally onto the device. The exact numbers may shift, but the logic for measuring them should not change. If thresholding affects the final decision, it must appear during validation too. If class imbalance matters in production, the evaluation script should expose it early, and if latency blocks release, the device harness should measure it before users feel the delay. Good teams make the evaluation process explicit and repeatable. That lets them compare versions honestly, explain trade-offs clearly, and prove that a model is ready for deployment rather than just ready for a chart. The safest habit is to check both quality metrics and runtime metrics before shipping. A model that cannot run within budget is not usable, no matter how good the offline score looks. That repeatability protects both release time and later updates. The same rules can be applied again after a firmware or model change, so the team is measuring the same thing each time instead of guessing. Evaluation means asking different questions with different checks, not chasing one score. On edge systems, that matters because a model can look strong in a clean lab setup and still fail under noise, limited power, tight memory, or a shift in the real environment. A single headline number hides too much. Good evaluation separates conditions, measures the failure modes that matter, and shows where a model is strong or fragile instead of pretending every deployment setting is the same. The first safeguard is clean data separation. Once training, validation, and testing are distinct, each split has one job, and the final test can remain a genuine measure of generalization. Training is for learning patterns, validation is for choosing settings like thresholds or stopping points, and testing is for the final estimate. If the test set gets used during development, it stops being an honest holdout and starts acting like another tuning set. That discipline gets even more important on edge projects, where it is tempting to keep checking one more idea against the same data. Every extra look makes the test result less reliable, so it should stay untouched until the end and then be used once under the chosen protocol. A single split can be misleading, so repeated resampling gives a better view of stability. By changing the train and validation partitions and comparing the results, you can see whether performance is steady or depends too much on one lucky split. Cross-validation is useful when data is limited or uneven. It tells you whether the method itself is solid or whether the score is being inflated by an easy partition of the data. Cross-validation still does not replace the final test set. Think of it as a way to measure uncertainty during development, especially when a model swings widely from fold to fold and one good score may just be sampling luck. An overall average can hide a serious weakness. The next step is to break results apart so the important subgroups are visible, not buried inside one aggregate number. Subgroup slicing matters because a model can look fine overall and still fail badly on one slice of the world. That can mean a site, a weather condition, a device type, or any metadata that changes how the model behaves in deployment. For Riverwatch Node, the useful question is not just whether the average score is good. The team needs to know whether the model breaks down after heavy rain or on one watershed, because those are the cases that matter before unattended monitoring goes live. The same logic applies to vehicle classification. If one body style or make is consistently misread, subgroup metrics expose that error pattern, and the evaluation starts caring about the cases where the model is systematically unreliable. Class imbalance can make a metric look better than the system deserves. The next concern is whether the chosen score is really sensitive to the classes that are underrepresented or costly to miss. When one class dominates, accuracy can stay high even while the model fails on the smaller classes. That is why the metric has to match the failure mode you care about, such as recall, precision, or false alarm rate for each class. A simple baseline test keeps the metric honest. If a random classifier that matches the class balance still looks acceptable under your score, then the metric is not separating real skill from nonsense very well. Real deployment usually has more than one success condition. After quality and error analysis, the evaluation has to include the resource limits that decide whether the model can actually run on the target device. Edge AI often trades accuracy against latency, memory, battery draw, or heat. A slightly better model that cannot meet the device budget may be less useful than a smaller model that runs reliably. Metric choice should follow the product requirement, not abstract preference. If fast response matters, latency must be measured. If the device is constrained, memory must be checked alongside predictive quality. If power savings by practical deployment, that trade-off deserves real weight. Some failure modes are too rare or too dangerous to wait for in the real world. When that happens, synthetic cases can expand coverage and let the system be stressed before a real incident occurs. For an anomaly detector, real examples of catastrophic failure may be scarce. Artificial edge cases, distortions, or simulations can fill that gap enough to test how the system reacts under unusual conditions. That help has limits, though, because a synthetic case can be too clean or too unlike the real environment. It should widen the test surface, then be checked against real labeled evidence whenever that evidence can be collected safely. Streaming systems add another layer. Raw model output is not always the final decision. The important question becomes how to turn a stream of scores into a stable action. In keyword spotting, the model may emit probabilities every few milliseconds, but the application still needs post-processing. Filtering smooths spikes, thresholding decides when the keyword is present, and debouncing prevents one utterance from firing repeatedly. That tuning is best done in the lab with labeled recordings. By running the stream over a long sample and adjusting the filter width, threshold, and debounce rules, the team can calibrate the decision logic before relying on it in the field. Good edge AI work depends on judgment about evaluation, not just model training. The practitioner has to protect the holdout, estimate variability, inspect subgroup behavior, challenge weak metrics, weigh resource trade-offs, probe rare cases, and calibrate streaming decisions before shipping. Evaluation is about making shipping decisions, not collecting a score. The methods in this part show how to judge a model for robustness, fairness, and real deployment constraints. Validation is where model choices get compared, thresholds get tuned, and pre-processing gets tested. The test set stays separate so it can give one clean estimate after the design is settled. A model can look fine on one split and still fail when the real world shifts. Field conditions like seasonal drift, sensor variation, and limited bandwidth force the evaluation to go beyond a single held-out score. These three stages play different roles. One supports development, one protects final judgment, and one keeps the system honest after the environment starts changing. Validation is where the development choices happen, while test data is reserved for the final check. After deployment, new data should come back as fresh evidence, not as a way to recycle the original holdout. That separation is what makes an evaluation credible. Once test data is used for everyday tuning, it no longer tells you how the model will really perform after release. Cross-validation checks whether the result depends too much on one lucky split. It gives a clearer picture of whether the model has learned a stable pattern or just fit the data partition it happened to get. By rotating through folds, you can compare performance across several views of the same data. Small variation is reassuring. Large swings suggest the model may be sensitive to chance or overfitting to quirks in one split. Edge projects often have limited labels and uneven coverage, so a single split can flatter a model by accident. Cross-validation helps expose whether the model is dependable enough to trust on a constrained device. Average performance can hide where the model breaks down. Breaking results into subgroups makes the weak spots visible instead of leaving them buried inside one overall number. A strong total score can still cover serious mistakes in smaller slices of the data. Looking by type, site, or operating condition shows whether the model is really working across the cases that matter. The kind of slice-by-slice view is how you check fairness and coverage without guessing. It also gives you a way to explain the risk profile of the system to different stakeholders, not just the average metric. Imbalanced data can make a weak model look better than it is. When one class dominates, accuracy may reward the system for ignoring the rare classes that actually matter. A model that predicts the majority class most of the time may still score well on accuracy. That is why one summary number can hide total failure where the dataset is least balanced. A poor baseline is a good sanity check. If it gets almost the same score as the trained model, the metric is probably not sensitive to the errors you care about. Different mistakes have different consequences, especially on a constrained device. A false alarm might waste energy or trigger alert fatigue, while a missed event may be far more serious. So the evaluation has to weigh those costs directly. Deployment is usually a balancing act across several constraints at once. The useful model is not just the one with the best score, but the one that fits the hardware, timing, and quality requirements together. A model that wins on raw accuracy can still be the wrong choice if it is too slow, too large, or too expensive to run. On the other hand, a tiny model may fit the device, but fail on the rare cases that matter most. Those trade-offs are part of the design problem itself, not an afterthought. The team has to understand why a slightly weaker model might actually be the safer choice once real-time response and device limits are included. Rare or dangerous events often need synthetic cases to get enough coverage for testing. The important point is that synthetic data widens the test envelope, but it does not replace real evidence from the field. Generated examples are useful when the real event is too rare or too risky to wait for. They let you inspect how the system behaves under failure conditions and whether the fallback logic responds the way it should. A generated case can resemble the real one only in broad shape. Field data is still needed to catch the messy artifacts, timing issues, and interference that synthetic examples usually miss. Recorded lab data gives you a faster way to tune the full decision pipeline before deployment. It is especially useful when the post-processing steps matter as much as the model output itself. For streaming systems, replaying labeled audio or sensor data lets you test thresholding, filtering, and debouncing without waiting for live traffic. That makes it easier to see whether a brief spike becomes a useful trigger or just noise. Recorded streams give quick feedback on the whole decision chain, not just the raw model score. They still miss some real-world variation, so the right workflow is to calibrate from recordings, deploy cautiously, collect fresh evidence, and adjust again. Strong evaluation combines all of these habits. Protect the holdout, probe stability with cross-validation. Inspect subgroups, watch imbalance, balance competing costs, and use synthetic and recorded data carefully before trusting the model in the field. Evaluation is where responsibility becomes measurable. The real question is whether a system is fit for the environment where it will actually operate, not just whether it scores well in a controlled test. A polished test score can hide real deployment problems. In Edge AI, the device, the sensor setup, the noise, and the users all shape behavior. So a model that looks strong on paper can fail once conditions shift. Riverwatch Node makes that gap easy to see. Water conditions, battery wear, sensor drift, and weak connectivity all change what the model faces, so the evaluation has to ask whether the system still helps the right people under real constraints. The next step is to separate dataset performance from deployment performance. A model can be accurate on collected data and still behave differently once hardware, location, and users introduce new conditions. That difference matters because edge systems do not run in one fixed environment. Hardware limits, thermal effects, sensor quality, weather, and user habits can all shift the outcome, even when the input looks similar. A single overall metric can be misleading when the important cases are rare. If the model misses the exact event it was built to catch, a high average score does not protect you from the operational cost of that miss. Subgroup analysis exposes where the average is hiding risk. Once performance is split by region, sensor type, or operating mode, the weak spots become visible and the evaluation becomes much more trustworthy. A Riverwatch node model might do well in calm weather and still struggle when rain, occlusion, or other field conditions appear. That kind of gap is not a small detail. It can decide whether people trust the system at all. Responsible evaluation asks which groups and conditions are covered by the data and which are missing. If one subgroup carries more of the harm from errors, that group needs closer scrutiny because the real cost may be a missed alarm, a false dispatch, or a safety issue. The data pipeline is part of the evaluation system itself. If labels are weak, sampling is narrow, or difficult cases are missing, The score can create confidence that the model does not deserve. Evaluation can only be as good as the data behind it. When the training and test sets miss the hard cases, or when labels ignore important distinctions, the metric starts rewarding the wrong behavior. Engineers can build a metric, but domain experts define the meaning of success. They know which mistakes are acceptable, how quickly a response must happen, and what a useful warning looks like in daily operation. Freshline Inspector shows why release discipline matters. A model can uncover a useful pattern and still introduce risk if rollout is not versioned, monitored, and controlled before it becomes part of normal operations. Responsible AI becomes concrete at the evaluation step. Choices about representation, labeling, and subgroup coverage are ethical choices because they decide whose experience shapes the system and whose risk gets overlooked. If a site, device class, or user group is missing from the data, the model gets tuned for the easiest cases. That creates foreseeable harm, and it is avoidable when the gap is caught early. The same error can matter very differently from one setting to another. A missed event, a false alarm, or a short delay may be acceptable in one workflow and unacceptable in a safety-sensitive one. So the evaluation plan has to reflect those boundaries. Deployment is not the end of evaluation. It is the point where new evidence starts arriving. The system meets real conditions only after release, so the job becomes learning how it behaves under production constraints. A rollout should be treated as a transition into production, not a ceremonial handoff. Once the system is live, it faces realities that no lab setup fully reproduces, and that is exactly why evaluation has to continue. Live evidence tells you how the model behaves on real devices, with real users, and across changing conditions. From there, the questions are practical. Is any subgroup underserved? Has the environment shifted? And does the system need adjustment or retirement? That expectation reaches beyond the classroom and into the workplace. Teams value people who can connect test results to operational risk and explain why a model is trustworthy, where it is weak, and what evidence should come next. Once the system is live, the work shifts toward monitoring, feedback, and long-term support. The real question becomes whether the system keeps its fit as conditions evolve, because that is what responsible evaluation is really protecting. Evaluation is part of deciding whether an edge AI system should exist and what limits it needs to be used safely. The point here is not only model quality, but the risk of harm when the system leaves the lab and meets real conditions. Responsible evaluation should change decisions, not just produce a score. It helps teams see hidden failure modes, reduce production risk, and decide whether to proceed, constrain the system, revise it, or stop. A model can look strong on clean historical data and still fail on a riverbank with mud, seasonal shifts, or weak radio links. That gap matters because it can lead to missed warnings, nuisance alerts, and trust that erodes once the system is deployed. The first question is what problem is being solved, for whom, and in what environment. Once that context is clear, the metric becomes a tool instead of a distraction. If the goal is to support inspections in a remote watershed, accuracy is too blunt by itself. Missed detections, false alarms, battery drain, and recovery after connectivity returns may matter much more than a single overall score. Operators, local staff, and environmental specialists know which errors are costly and which conditions never appear in the data. Their input makes evaluation about usefulness, safety, and fit instead of only statistics. Averages can be misleading when a model behaves differently for one site, one sensor setup, or one rare condition. The job here is to look past the overall number and ask where the system is weak. A model may look stable across the whole dataset, while doing poorly on a specific stretch of river or a rare weather pattern. In imbalanced tasks, the majority class can make performance look better than it really is for the cases that matter most. That question turns fairness into operations. A detector that handles common events well, but misses winter ice formation can still fail at the highest consequence moments, even if the overall score looks strong. Evaluation cannot be more trustworthy than the data behind it. When the dataset is stale, skewed, incomplete, or narrowly collected, the metric may look precise while hiding important problems. The dataset defines what the model could learn and what the evaluation can reveal. If the data is weak, the result can look scientific without being dependable. Small choices in data construction matter a lot. Leaving out nighttime conditions, rare species, or low connectivity periods can make a field-ready system look stronger than it really is, which creates overconfidence. A deployment example makes the difference between test data and real use much easier to see. Once a device is on site, it faces conditions that no clean split can fully capture. A system validated on typical stream activity still has to handle changing water levels, mud on the sensor, battery swings, intermittent network access, and human workflows. Those are the pressures that expose whether the model truly fits the environment. Live use can expose harmful errors, like reacting to harmless debris or missing storm surge patterns. It can also teach the team practical things, such as better thresholds or different maintenance timing, so the field itself becomes evidence. A live system keeps testing its own assumptions. Some assumptions still hold, some have weakened, and some never matched reality as well as the lab suggested. Hiring teams usually look for more than a model score. They want people who can connect metrics to consequences, reason about field constraints, and make release decisions that balance performance with risk. A strong practitioner explains what a result means for users and for the system around it. That includes deciding on a rollout limit, asking for more testing on a subgroup, or recommending a staged release when the evidence is still thin. The other half is what the result means for deployment, support, and risk. Those skills are not extras. They are core, edge AI competencies. A simple livestock example shows why field evidence matters. A model can look acceptable in testing and still reveal new patterns once real users and real conditions appear. After release, the team noticed that many misses clustered around certain lighting conditions and animal positions. The same deployment also showed which alerts were useful to ranch staff and which ones only added noise. That outcome does not mean the model was useless. It means testing alone could not finish the evaluation story because real use exposed both failure and improvement opportunities. A model is responsibly evaluated only when its behavior is understood in context, across relevant users, and in conditions close to deployment. After that, live use becomes the next stage of evidence, showing what to improve, what to constrain, and when to intervene. Deployment starts with preparation, not with pushing software out the door. The focus here is how to turn a model change into a controlled operational decision. The core idea is that release planning deserves the same discipline as model training. If the plan is weak, even a good model can become a bad field release. A field rollout should be handled like a pre-flight check. The team defines success, looks for failure points, plans recovery, and gets the right people aligned before any device changes. A narrow objective makes the result interpretable. If the team mixes scaling, replacement, and calibration all at once, a later issue becomes hard to trace back to its real cause. Good deployment metrics cover two sides of the system: how well the model performs and how well the device behaves in the real world. A strong test score means little if the unit drains power, wakes too often, or falls apart under noise. Edge systems are hard to evaluate after they go live because labels, connectivity, and conditions are all less convenient in the field. That is why verification has to happen early, under realistic stress, before the site becomes the place where basic failures are discovered. Risk review turns technical testing into operational responsibility. The team needs to know what can fail, how serious it would be, and exactly how to stop, constrain, or roll back the release if the field conditions change. Rollout design is a plan choice. Which version, how many devices first, which sites, and whether the change is staged or automatic. A small pilot limits damage, while automation only helps when it follows a careful plan. A rollout slice has to represent the conditions that matter, not just the easiest cases. If geography, hardware, or user groups are left out, the release can look healthy while an important segment quietly fails. Communication belongs in the control loop because local teams see constraints that dashboards miss. Maintenance windows, outages, and seasonal changes can all affect the deployment, so the plan has to absorb that input early. All of these steps lead to one go or no-go decision based on evidence and constraints. If the objectives, metrics, risks, recovery plan, or stakeholder input are still unclear, the responsible answer is to hold the release. The ability to translate model changes into safe operational choices matters a lot in edge and IoT work. It protects devices, schedules, power budgets, and trust in the system, which is exactly why hiring teams value it. Riverwatch Node puts the process into practice by narrowing the goal, choosing metrics for both model quality and device behavior, and starting with a small site slice. Rollback steps and stakeholder messaging are ready before release, so a river change or sensor problem does not force improvisation. Pre-deployment work turns an edge AI release into a managed decision, not a guess. The focus here is on objectives, risk, metrics, and approval before the system ever reaches the field. The same theme carries through the planning details. A system should earn its release by showing clear goals, clear evidence, and clear safeguards. A live edge system carries operational costs, dependencies, and failure modes. So release decisions need the same discipline as any other important production change. The team has to know what success looks like, what could fail, and who has to agree before the system goes live. Good objectives are specific enough to measure and limited enough to interpret. If Riverwatch Node is supposed to miss fewer flood risk alerts, save power, and cut unnecessary traffic, those goals need to stay distinct so the team can tell what the release actually improved. A strong test set score can hide a weak field system. Accuracy, precision, and recall matter, but so do alert volume, latency, memory use, power draw, connectivity, and device health, because a model that overloads operators or drains batteries is not a successful deployment. Pre-deployment checks try to expose where the lab is too clean. Changes in turbidity, sensor drift, low light, or intermittent connectivity reveal the gap between controlled testing and the messy conditions the system will face outside the lab. A risk review should say exactly what can go wrong and what the team will do about it. If false positives rise at one site, the answer might be tighter thresholds, suppression rules, or manual review, and the stop rule should tell everyone when a rollout has crossed the line. Recovery is bigger than reverting code. In the field, rollback may mean restoring a prior version, resetting a threshold, replacing a bad firmware package, or reintroducing a manual process while someone investigates a problem. Those design choices shape the evidence the team will get after release. A controlled rollout to one production line, for example, lets Freshline Inspector prove itself with limited exposure instead of placing every plant under the same risk at once. A narrow pilot can miss the very problems that matter later. Different sites, mounting setups, weather patterns, shift timing, or vibration levels can change the signal enough to expose failures that a uniform first cohort would never surface. A release decision should be based on whether the objectives still make sense, the metrics support the change, the risks are bounded, and recovery is ready. When the evidence is unclear, holding back is a valid technical choice, not a delay for its own sake. Ethical review needs to ask whether the system behaves unevenly across locations, groups, or operating conditions. Unequal false alarms, delays, or burden can hide in the environment, so the lab result alone is not enough to clear the deployment. Deployment planning works best when stakeholders can raise the constraints that the engineering team might miss. Maintenance windows, harvest periods, shift changes, fragile devices, and weather alerts can all force the schedule to change before rollout becomes expensive. For Riverwatch node, that may mean waiting for access and maintenance windows. For Freshline Inspector, it may mean avoiding peak production. The practical point is that operational coordination belongs in the release plan from the start. Employers look for people who can connect model work to production responsibility. The strongest engineers can explain how a metric affects release decisions, how a staged rollout reduces risk, and how monitoring and recovery keep the system usable in real industrial, healthcare, and IoT settings. A release is ready only when the team can defend why it exists, how success will be measured, what could fail, how it can be recovered, and who has to be involved. Without that full picture, the system is not ready for live deployment. Deployment is the start of supervised operation, not the end of the hard work. The focus shifts to watching the system in the field, coordinating people, and stepping in when behavior changes. A system in production faces real weather, real users, and real operating conditions, so the team has to treat deployment as an active period. Lab results matter, but they never capture every field condition. The rollout needs a clear communication path, so the people affected know what is changing and how to report problems quickly. That visibility turns deployment into a managed process instead of a blind push. Operators, technicians, supervisors, support staff, and sometimes end users all need enough detail to act at the right moment. If something goes wrong, fast reporting only helps when everyone knows where to send the signal. For a field system, that means giving crews a short list of sites, the issues to watch for, and the exact channel for escalation. The goal is to cut the time between noticing a problem and getting the right people involved. Staged rollout reduces risk by letting the team learn from a small release before the full fleet is exposed. It also makes it easier to tell whether a bad result comes from the model, the site, or the environment. A narrow first release gives the team a small blast radius and a clean comparison point. If the first devices behave well, that early evidence supports a broader rollout. A few well-chosen sites can tell you a lot before the system reaches harder-to-recover locations. That matters for any edge deployment where mistakes can affect operations, quality, or safety. Version tracking tells you precisely which software and rules are active on each device. Without that record, diagnosing a problem or rolling back safely becomes much harder. That inventory is more than administrative detail. When hardware is hard to update, knowing the exact state of each device becomes part of keeping the fleet safe and understandable. A remote node may sit in the field for a long time with no easy path for patching, so the team has to know exactly what it is running. Otherwise, a strange behavior can be blamed on the wrong software state and never get fixed correctly. That set of details gives you a real rollback target instead of guess. If the inventory is incomplete, you may know something is wrong without knowing what to return to. Monitoring works by comparing the live system against the baseline the team expected before release. Metrics only become useful when they are judged against a known normal pattern. The team should already know what normal looks like: latency, alert volume, confidence ranges, and typical error patterns. Once the system is live, Those signals need to be interpreted against that expectation, not in isolation. If a deployed site suddenly becomes quiet when it should be producing alerts, that change might point to the model, the sensor, the threshold, or the pipeline. The important part is that live behavior has drifted from expectation, so the team has a concrete trigger to look deeper. When behavior diverges, the first move is to stop the rollout from reaching more devices. After that, the team can investigate the cause and decide whether the system needs to be restored to a known good state. Freezing the rollout protects the fleet and preserves the evidence around the problem. Then the team can check whether the issue is tied to one site, one firmware family, one threshold, or one user workflow. Rollback is not defeat. It is the responsible choice when behavior looks harmful or too far off target. Returning to a known state buys time to stabilize the deployment before trying again. Edge systems can keep acting even when no one is standing beside them, so intervention has to happen early. If the model could damage equipment, disrupt service, or create unsafe decisions, waiting for a larger incident is the wrong trade-off. These are the skills that matter in production support and ML reliability work, because a deployment succeeds only if the field can be controlled. Good engineering is not just building a model. It is managing what happens after release. A safe edge AI rollout is managed actively in the field from start to finish. The team keeps people informed, limits exposure, tracks exactly what runs where, and responds quickly when reality stops matching the plan. Deployment turns design decisions into real-world behavior, so the hard part is no longer the model alone. The focus here is on what changes when a system leaves the lab and starts affecting people, devices, and operations. Plans look clean on paper, but live systems bring uncertainty, exceptions, and partial failures. That gap between intention and reality is exactly why deployment needs careful control. A release is not just a software handoff. People have to know what changed, the rollout has to be controlled, the fleet state has to be tracked, and live behavior has to be checked against what was predicted before release. That communication starts before any device updates. Field staff and operators need clear expectations, and they also need a path to send back observations, because early field reports often reveal problems the lab never exposed. A stage rollout is a way to control risk while preserving the ability to learn from the first release group. It helps isolate where a problem begins instead of spreading that uncertainty across the whole fleet. Releasing to a small subset limits the blast radius if something goes wrong. If the first sites behave differently, the team can narrow the cause to a site condition, a device class, or a version conflict before more systems are affected. That same approach works when the release changes thresholds or filters. Small changes in behavior can expose whether the system is now too sensitive, too delayed, or filtering away too much signal. Mixed fleets need exact version records because not every device can be updated in the same way. When a problem appears, the team has to know which versions are actually running and which devices were left behind. That record keeping keeps the fleet understandable over time. Without it, safety reviews and troubleshooting turn into guesses instead of evidence-based decisions. Live monitoring only works when the rollout is compared to the behavior the team predicted beforehand. The question is not whether a number looks good in isolation, but whether it matches the expected direction and magnitude of change. A rollout review needs a benchmark, otherwise the numbers have no meaning. If the expectation was fewer false alarms with only a small change in misses, then the live result has to be judged against that target, not against a vague sense that the metric is high or low. One metric can hide the real cost of a deployment. A classifier might look better on precision while becoming slow, power-hungry, or frustrating for users because the rest of the operating signals are drifting the wrong way. That matters most for rare failure systems and imbalanced classifiers, where a single flattering score can conceal a serious operational problem. The live question is whether the system is behaving the way the evaluation promised it would. When field behavior breaks from expectation, the response has to be fast and disciplined. The priorities shift from expansion to stabilization, so the team can protect users and understand what changed. The sequence matters. Pause to stop uncertainty from spreading. Investigate to separate a temporary glitch from a deeper flaw, and roll back to return to a known safe state if the evidence points that way. A bad field result is not something to wait out. If warnings are being suppressed, false alerts are rising, or battery life is collapsing, the safer move is to stop the rollout and contain the problem before it spreads. Legacy hardware makes version control even more important because some units cannot be updated once the issue is discovered. In that case, the team may need to limit what those devices do or remove them from critical roles altogether. That is why responsible AI belongs inside deployment practice, not off in a separate ethics folder. If staging, monitoring, and rollback can prevent foreseeable harm, then they are part of doing the job well. That is the daily work of edge AI in practice. The person doing this job has to manage versions, read signals, respond to incidents, and make decisions that keep the system useful without losing control of risk. The operating mindset is consistent. Keep people informed, roll out in controlled stages, maintain exact inventory, compare reality with the pre-release expectation, and stop the deployment when the system stops behaving as intended. That discipline is what keeps a live edge rollout safe enough to continue. Deployment marks the point where responsibility becomes continuous. The main job now is to communicate what changed, watch for problems, and document exactly what happened so the system can be trusted in real use. A live system needs attention right away because launch can hide delayed failures, unanswered questions, and lessons that only appear after people start using it. Treating deployment as a follow-up phase keeps the system dependable outside the lab. The first obligation after launch is clear communication. People who depend on the system need a plain update so they know what went out and what to watch for. That update should give the version, the deployment time, the main changes, and any likely risks. When support requests start arriving, everyone has the same reference point and confusion drops fast. A field team often spots early warning signs before the engineering team does. A short deployment summary plus a clear reporting path makes it much easier for those observations to reach the people who can respond. Monitoring does not stop when the system goes live. Real environments keep changing, and the first week can still hide problems that only show up under pressure. Edge conditions are hard to reproduce perfectly, so temperature, network issues, dust, vibration, power changes, and user habits can all shift behavior. Some failures are immediate, but others appear only after drift, aging, or workflow changes build up over time. That is why the team keeps observing after the first week. A calm pilot can still hide a slow failure mode, and post-deployment monitoring is what catches those surprises while they are still manageable. A deployment report turns the rollout into something the whole team can use later. It preserves the plan, the outcome, the surprises, and the response so the deployment can be reconstructed by someone who was not there. That record does not need to be long. It needs to be accurate. A short report can tell a later reader what was intended, what actually occurred, and what corrective action was taken. Good logs make comparison possible. When the next rollout behaves differently, the team can check the earlier record instead of relying on memory, and over time that reduces repeat mistakes. Support becomes part of the job once the system is live. The work shifts into answering reports, reviewing behavior, updating records, and deciding whether the system should keep running as it is. Devices age, data changes, users change, and rules can change too. Because edge systems live in that moving environment, support has to include monitoring, escalation, and disciplined record keeping. If nobody is watching, a system can become less accurate, less fair, or less useful without anyone noticing. The risk is not only technical, because a system can keep making decisions long after the conditions that justified it have disappeared. Responsible deployment always leaves room for revision, constraint, or retirement. Leaving a system unsupported is an active choice to let risk accumulate without supervision. Employers look for people who can handle the real work after a model ships. Careful documentation, clear stakeholder communication, and fast production troubleshooting matter just as much as building the model itself. Teams value engineers who can bridge machine learning, operations, and field reliability. Those roles sit at the intersection of software, hardware, and real-world constraints, so post-deployment skill becomes a major part of professional value. The practical lesson is that launch starts the proof phase, not the finish line. A responsible team keeps communicating, monitoring, documenting, and deciding when a system needs repair, limits, or retirement, because support quality is part of safety and trust. Post-deployment work is where the model starts affecting real systems. So the focus shifts from training to what the application does and what it means in practice. The important questions now are reliability, risk, and the effect on the people or process using it. Post-deployment work is where responsibility becomes visible. Once an edge AI system is live, the real question is no longer whether it launched, but whether it can be supported, observed, and corrected safely. A live system needs communication, observation, documentation, and readiness to act. If the rollout ends and support does not begin, the team loses control of how the system behaves in the field. People around the system need clear status updates because they're often the first to spot trouble. A good communication plan names the active version, the expected behavior, the limits, and the path for reporting odd outputs or failures. Riverwatch Node shows why that matters in a field setting. The team keeps staff informed about the revision at each site and leave a low bandwidth channel open, so warnings from storms, false alerts, or strange device behavior reach the right people quickly. A system can look stable during testing and still fail later when seasons shift, hardware ages, or users change how they work. Monitoring has to continue after launch because drift often shows up only after enough real use has accumulated. A deployment report makes the rollout traceable. It records what was intended, what actually happened, what surprised the team, what was changed afterward, and which version and constraints were in force. Long-term support is more than fixing bugs. It includes maintenance, performance checks, and a hard judgment about whether the model still fits reality, because a drifting system can become unreliable, unfair, or unsafe. Responsible teams treat support as an ongoing life cycle. Sometimes the answer is a patch or retraining. Sometimes it is tighter limits on use. And sometimes the right decision is to turn the system off if safe support cannot be sustained. That is why edge AI jobs demand more than model building. Employers need people who can keep production evidence organized, communicate with stakeholders, and tell the difference between a successful demo and a system that can actually be supported. The lasting measure of an edge AI system is not just whether it launched cleanly, but whether it stayed accountable afterward. Communication, monitoring, documentation, and ethical follow-through are part of putting intelligence into the world responsibly. Monitoring begins the moment a model leaves the lab, because field conditions immediately change what the system sees and how it behaves. The goal here is to understand how to observe a live edge deployment well enough to trust it, fix it, and keep improving it. Once the model is outside the lab, the environment stops being controlled. Lighting shifts, users behave differently, and new failure modes appear. So support has to start immediately and continue for the whole lifetime of the device. If you cannot observe the system in the field, you cannot really know how it is performing. The first question is not what data would be ideal, but what feedback is actually available. Different devices expose very different levels of visibility, and the whole monitoring plan has to fit that constraint. A connected device may return samples, logs, and outcomes, while another can only report tiny telemetry messages. In the hardest case, raw inputs never leave the device, so user reports become the only signal left. That is not a minor limitation. It shapes whether the deployment is even responsible. A rollout can start with generous connectivity and then tighten later as bandwidth gets expensive or the site becomes more remote. Early on, raw readings and snapshots may be realistic. Later, summaries and anomaly alerts may be all you can afford. Good monitoring adapts to that shift instead of pretending the links stayed the same. A standardized, centrally supported fleet is easier to inspect, so the monitoring can be more disciplined. Even there, the real question never changes: what evidence can be observed and what can be inferred from it? The best starting point is the strongest signal that is still safe, legal, and practical to collect. When raw data is available, it usually gives the clearest explanation of model behavior. Raw inputs preserve the actual field conditions, so they're often the fastest way to understand why predictions look the way they do. Even a small batch from the real world can expose training mismatch or show that one edge case appears far more often than expected. Sampling should be intentional, not indiscriminate. A random trickle gives broad coverage. Periodic samples help with trends, and uncertain cases are especially valuable because they often reveal brittle parts of the model or conditions the lab never covered. When bandwidth and power are tight, full samples may be impossible, but tiny status codes, drift flags, or compact measurements still give useful visibility. The point is not volume. The point is getting enough signal to know whether the device is healthy and the model is still behaving plausibly. Privacy-sensitive devices need a hard boundary around what leaves the device. If raw video or other sensitive input is the reason for edge inference, monitoring has to respect that promise and rely on safer signals like counts, confidence summaries, or event metadata. When raw data is unavailable, summaries become the next best layer of evidence. Distribution changes can still reveal that the world around the model has shifted, even if you never see the original samples. Simple aggregates like means, medians, and spread are often enough to spot mismatch between development data and field data. They do not tell the whole story, but they can quickly point to drift, regression, or a change in operating conditions. A degraded signal can still be informative. Thumbnails, grayscale images, selected channels, or moving averages may lose detail, but they still show which patterns are present and whether the environment has shifted enough to matter. The model's predictions deserve the same kind of attention as the inputs. If the output mix changes sharply after an update, that can point to a bug, a broken pre-processing step, or a real shift in the deployment environment. Output monitoring is also a practical regression test. A sudden, implausible change in prediction shape usually means something in the model or the surrounding code has changed, and that is exactly the kind of change worth catching early. Predictions alone do not explain behavior in the field. Logs and device state add the operational context that turns raw model output into something you can interpret correctly. A log can show uptime, power draw, sensor faults, or repeated user actions, and those details often explain poor performance better than the predictions do. What looks like model failure may actually be hardware trouble, misuse, or a mismatch with the real workflow. A device can produce reasonable predictions and still be unhealthy in practice. It may drain batteries, overheat, or keep restarting. So the monitoring surface has to include operational state, not just inference output. When connectivity is limited, decide ahead of time which state facts are worth saving. Even a small record of restarts, battery thresholds, or user overrides can make the later diagnosis much clearer. Some systems influence a downstream process, so the real measure of success lives beyond the prediction itself. In those cases, the output matters, but only as one step in a longer chain of effects. A device that reduces waste, improves crop quality, or changes user behavior has to be judged by what happens afterward. The model can be correct internally and still miss its purpose if the downstream process does not improve. That is why outcome tracking matters. You need evidence that the recommendation was followed, accepted, or effective, not just evidence that the model produced the right class or score. For shipment damage, health, or fitness applications, the important question is whether the prediction correlates with real losses, returns, habits, or claims. Internal accuracy and real-world impact are linked, but they are not the same thing. User reports can fill gaps that telemetry cannot reach, especially when the device has little or no return channel. The challenge is that those reports are useful evidence, not pure ground truth. When a device cannot send data back, people using it may still tell you whether it behaved well, missed an event, or created extra work. Those reports are often the only way to see problems that telemetry cannot capture. User feedback has to be interpreted carefully because people are busy, cautious, frustrated, or affected by workplace incentives. That social context does not make the feedback useless. It means the signal needs structure and judgment. Specific questions make feedback much more usable. It is better to ask whether something was late, early, correct, but unhelpful, or simply the wrong action, because those answers can be compared over time and combined with other monitoring data. Monitoring should feed both immediate debugging and future data collection. The same evidence that explains a live problem can also show what the next training set needs to include. Hard or ambiguous cases may belong in the next training or evaluation set. Logs, output shifts, and user workarounds all point toward the same goal: collect better evidence from the conditions the model actually faces. Selective sampling creates a learning loop. The examples that confuse the model most are usually the ones worth studying first, because they can guide retraining, threshold changes, or better fallback behavior. Monitoring is not the same as retraining, evaluation, or support tickets. It is the practice of watching a live system through the channels that remain available, then using that evidence to decide whether the system can continue as it is or needs help. If nothing can be observed, not samples, not summaries, not logs, not outcomes, not user reports, then the deployment is no longer responsibly supportable. In Edge AI, the ability to keep learning from the field is what separates a fragile prototype from a trustworthy product. Post-deployment monitoring starts the moment a model reaches the field because deployment changes what evidence is available and what decisions you can make from it. Field monitoring has to work within real limits. Weak connections, changing environments, privacy concerns, and partial visibility into what the device actually sees. A live model no longer sits in a clean lab setting. It has to be judged from messy real-world signals. That means the monitoring plan has to account for incomplete labels, variable conditions, and devices that can only report a slice of the input they saw. The richest evidence is the original input, because it lets you inspect exactly what reached the model. When full upload is too costly or too sensitive, selective snapshots and uncertainty trigger captures still give enough material to spot drift, noise, or a mismatch between training data and the field. Reduced telemetry can still be very informative. Averages, counts, threshold crossings, and confidence summaries cannot show every failure, but they can reveal sensor degradation, changing behavior, or a bug that appeared after a model update. Raw data helps debug a specific case, while summary signals help detect drift over time. If the live input distribution shifts, the monitoring data tells you that something changed, even if it cannot tell you immediately whether the cause is environmental, operational, or a deployment error. Logs tell you which model ran, whether inference completed, and whether the system fell back or failed. Outcome measures go further and show whether the device actually helped in the world, which is why production monitoring matters more than a nice dashboard. A device with very little bandwidth can still report useful warnings through counts, confidence summaries, and selected edge cases. Those small signals are often enough to show that thresholds no longer fit the environment, even when the raw signal cannot leave the device. People on the ground often see workarounds, delays, and confusing behavior that automatic logs never capture. Those reports are valuable, but they need to be compared across users and matched with telemetry before drawing conclusions. Once a signal appears, the response can range from ignoring expected noise to investigating a drift event, tightening operating limits, rolling back a release, or retraining the model. Severe problems can justify taking the system out of service until it is redesigned. Monitoring is a production engineering skill as much as an ML skill, because the hard part is collecting the right evidence under power, privacy, connectivity, and recovery limits. Once the system is deployed, those constraints define what you can know and what you can safely do next. A live-edge system changes the rules of improvement. Once devices are deployed, every update has to respect limited bandwidth, offline units, mixed firmware, and the risk of causing a fleet-wide problem. Development lets you change quickly and compare results with little friction. Production is different. Every change has side effects, so learning from real usage has to happen with much tighter control. Field feedback works best when it is organized from broad evidence to narrow evidence. That order helps separate a real environment change from a model problem or a deployment fault. The first move is to collect the widest signals that can tell you something changed. After that, each check should focus the search a little more. Concrete examples are often the fastest way to spot trouble. A small set of odd images or sensor readings can reveal a seasonal shift, a new background condition, or a class the model never saw often enough. Those channels answer different questions. Inputs tell you about the world, outputs tell you about the model, outcomes tell you whether the job is being done, and user reports tell you how the system feels in practice. A metric only matters when you know what changed around it. If inputs look stable but outputs shift, the issue may be in the device pipeline or runtime. If inputs have changed, the field may simply be showing new conditions. The important split is between the world changing and the system breaking. That distinction tells you whether to update the data, fix the implementation, or both. Data drift means the environment has moved. Output drift means the prediction pattern has changed. An implementation fault means the intended model or pipeline is not being executed correctly. A seasonal shift might point to water color, lighting, or debris patterns changing in the field. But if the inputs still resemble older samples and the outputs change after a software push, the smarter suspicion is a version mismatch or runtime bug. A model can look healthy overall and still fail a specific region or condition. The fix is to expand the data around the weak area and test whether coverage, thresholds, or features need to change. Production feedback becomes most useful when it feeds the next dataset, not when it sits in logs. The field should tell you which examples deserve more attention and training. Hard examples, weak subgroups, and rare but critical events all deserve deliberate collection and labeling. That is how field experience turns into better evaluation and better coverage. The goal is not to pile up logs. It is to choose the cases that teach the model where it is weakest. That matters most when one class is rare and easy to miss behind a good overall accuracy score. Active learning can work in production when the deployed system helps pick the next samples to label. The value is a tighter feedback loop, but only if the selection process stays controlled. Low confidence outputs and unusual failures are often the most informative cases to review. They point the next dataset revision toward the samples that matter most for improving the model. That process can also distort the data if it is left unchecked. If only noisy sites or loud complaints drive collection, the model learns the wrong population, so the sampling plan has to be audited. Version history is part of the diagnosis. Without it, a mixed fleet becomes hard to debug because you cannot tell which hardware, firmware, model, or backend produced a result. Those records give each prediction a place in the system history. They're what let you trace a fault back to the exact configuration that produced it. If one device group behaves differently from another, the cause may be a specific firmware model pairing rather than the model alone. Exact version records let you isolate the change and decide whether to roll back, patch, or revalidate. A required baseline can improve safety and consistency, but pushing it too hard can break offline sites or slow adoption on constrained devices. Improvement here is a balance between reproducibility, safety, and rollout speed. These are the same skills that show up in production AI roles: finding field issues, managing staged updates, and proving that a change improved the system rather than just changing it. Real operations work connects field symptoms to version history and then to a safe update plan. The person who can do that is doing practical production ML work. A deployed system improves by reading the right signals, expanding the right datasets, revising the right algorithms, and keeping every version visible. That is how the system gets better without losing control of itself. A deployed model changes the problem from getting it to work in the lab to understanding what it is doing in the field. The hard part is making changes carefully because a live system can fail in new ways when hardware, connectivity, or downstream services are involved. Once a model is running on real devices, every fix has to be treated as a live change, not a simple edit. The safe approach is to keep updates narrow, reversible, and justified by evidence from the field. Good diagnosis starts with organized evidence, not a guess. The goal is to stack different signals so each one helps narrow the cause of the problem. Start with representative inputs, especially edge cases and low-confidence examples. Then compare predicted outputs, technical health metrics, actual outcomes, and the reports from people using the system, because each layer reveals a different part of the failure. When these channels disagree, they point to different kinds of problems. Drift, threshold mismatch, device-side faults, and subgroup underperformance can look similar at first, but the pattern across channels often tells them apart. Diagnosis gets clearer when the live system is compared against the baseline from development. That comparison shows whether the issue comes from the data, the device, or the operating environment. A stream that no longer resembles training data may signal drift or a sensor change. If confidence drops only on certain devices, the implementation deserves suspicion. If predictions stay stable but outcomes worsen, the threshold may no longer fit the new setting. Riverwatch Node shows why this matters in practice. Winter and spring changed the stream in ways the lab data did not emphasize. That kind of shift is normal, so the system has to be monitored for it and designed to adapt safely when it appears. Production evidence does more than explain the current failure. It also tells you where the next improvement should come from. If a small seasonal slice causes most of the errors, more data from that slice is probably the best investment. If one device family lags behind, the model may be fine and the implementation may need work. The next step might be more data, a different threshold, a retrained model, a pre-processing correction, or a narrower rollout. Field evidence should decide among those options, because the easiest change is not always the right one. Live feedback can guide sampling the way active learning does, but only when the collection process is controlled. Uncertainty is useful, yet cannot be the only rule for what gets saved and labeled. Low-confidence cases are good candidates for review, but harvesting only those cases can skew the training set. That can amplify the model's blind spots and turn a bias reduction strategy into a bias reinforcement strategy. A safer policy saves borderline examples under explicit rules and checks them against outcomes before retraining. Coverage still matters, so the sample needs variety across noise, devices, and user contexts, not just the most obvious mistakes. Version records become essential when the fleet is not uniform. The first debugging question is often which hardware, firmware, model, and backend combination is actually running on a given device. When many revisions are active at once, the fault could live in the sensor stack, the runtime, the pre-processing code, or the service that receives the result. Exact version tracking keeps those possibilities separate instead of blurring them together. With version records, you can compare like with like, isolate the change that caused the fault, and decide whether to roll back or patch. Minimum version policies can improve safety, but pushing them too fast can break offline sites or overload constrained devices. Sustained improvement is a balance. Better accuracy should not come at the cost of usability, connectivity, or support burden. A good system stays manageable as it changes. A model can become more accurate and still become harder to operate if updates are too heavy or intervention is constant. The best plan protects the service as a whole, not just one metric on a dashboard. Strong engineers can read logs, compare field behavior with lab expectations, trace versions, and plan a rollout without destabilizing production. That mix of ML, reliability, IoT, and deployment support is what keeps a live system healthy. A deployed system needs ongoing monitoring, diagnosis, revision, and exact records of what is running where. That discipline is what keeps improvement real, traceable, and safe. Ethics and long-term support matter because good systems have to be trustworthy, maintainable, and safe over time. The real question is not only whether something works today, but whether it still serves people well when it grows, changes, and gets used in the real world. Long-term support turns ethics into an ongoing responsibility. The real question is not whether a system was acceptable at launch, but whether it still deserves to stay in service as conditions change. A deployed edge AI system enters a new phase once it leaves testing. Drift, device wear, rising maintenance cost, or a changed mission can all make yesterday's acceptable model questionable today. That means ethics has to be checked again and again, just like uptime or accuracy. If Riverwatch node starts missing incidents after seasonal change or sensor shifts, the issue is no longer just technical noise. It becomes a failure to serve the people depending on it. A responsible team decides ahead of time what will trigger a pause, rollback, constraint, or shutdown. Those thresholds should include safety misses, security problems, support limits, and field conditions the system was never built to handle. Even a stable deployment can become unacceptable when new evidence appears. A security finding, a stronger adversarial method, or a better model can show that the old system no longer fits the real world. Social expectations move too. Once local processing becomes practical, sending raw audio or video off device can start to look unnecessary, and a system that still collects that data may no longer match community norms. Meeting the law is only the minimum bar. A system can be legal and still be too intrusive or too risky, which is why responsible teams often set stricter standards than regulation alone requires. Edge systems are physical devices, so batteries, chips, enclosures, and materials matter over time. If repair parts disappear or disposal creates waste, long-term responsibility has to include replacement and safe retirement. When full service is no longer justified, the safer choice is controlled failure. The system can narrow its scope, fall back to a safer mode, or stop making high-stakes decisions while keeping the remaining value intact. That broader view matters because support decisions are not only about model accuracy. Privacy, obsolescence, and disposal can all push a product toward modification, migration, or retirement even when the code still runs. This responsibility sits with the people running the system day to day. They have to watch for harm, document deprecation, coordinate with stakeholders, and make evidence-based decisions about whether the system stays, changes, or shuts down. The continuing use of an edge AI system has to be earned with evidence. When drift, new risks, or changed expectations outrun the original assumptions, responsible support means revising the system or retiring it cleanly. Ethics and long-term support become central once a model leaves the lab, because deployment creates an ongoing duty to keep judging whether the system still deserves trust. Long-term support is about more than keeping a device running. It includes the harder decision of when to constrain it, when to revalidate it, and when to retire it. Once an edge system is out in the world, engineering turns into stewardship. The team has to keep asking whether the system is still fit for use, because safety and fairness can change as the environment changes around it. Edge devices often run with limited oversight, so they can keep producing outputs long after their assumptions have gone stale. That is why post-deployment reevaluation has to be part of the plan, not an emergency response. A system is still useful only while the drift is manageable, the costs stay reasonable, and the risk remains acceptable. A model can still work technically and still be the wrong choice to keep in production. Pre-committed stop conditions make action easier when something goes wrong, because the team already knows what should trigger pause, rollback, constrained operation, or retirement. Without that advanced decision, people tend to defend continued use just because the system is already embedded. A river monitor, an inspection model, or any other field system can fail simply because the environment shifts under it. Seasonal patterns, new defect types, and changing safety needs can all make a once-strong deployment no longer fit for purpose. Several kinds of change can force a new decision. Data drift, attacks, stronger algorithms, updated domain knowledge, and shifting social expectations. Support has to account for all of them because the failure may be technical, ethical, or both. A system can still be allowed by law and still become unwelcome to the people affected by it. Responsible support has to look beyond the legal floor and ask whether continued deployment still respects users and bystanders. A security review, a fairness audit, or new clinical evidence can expose a weakness that changes the status of the whole system. At that point, the right response may be to restrict it, revalidate it, or remove it from use. Ethical ownership also covers repair, replacement planning, battery handling, and disposal. If the hardware cannot be maintained without waste, or if end-of-life materials are likely to be mishandled, that belongs in the support decision too. When confidence drops, the safest move is often a narrower mode rather than a hard failure. A system can keep logging, alert a human, or limit itself to low-risk actions while the team investigates what went wrong. The ability to decide whether a live system should be kept, constrained, revised, or retired matters in regulated and safety-sensitive work. Being able to justify that decision and document the support plan is a strong professional signal. The practical discipline is to watch for change, Set stop rules early and respond when new evidence appears. Domain expertise, legal review, and user expectations all need a place in that judgment, because a system should stay deployed only while it still earns that right.